Good morning, everybody. Let's see if I can.
Good morning.
Good morning. Good morning. Let's see here. Very good. Yeah. There we go. Let's see. I'm going to share a screen here. Oops. So, good morning, everybody. So I put first a couple of announcements. You should have gotten an email from the safety department on campus, and if you want to do the lab, you have to comply with that. It's simple. Just sort of read a couple things and DocuSign a thing, and basically says you're not going to kill everyone else on the planet by spreading coronavirus rampantly. Yay. So there's that. And then what else was I going to say? Oh, also I put I did one more homework problem, and I put a little like 7-minute video of me solving it onto Canvas. So you can look at that there also. Let's see here. No, this sucks. I'm going to put this up here so I can see you all. What is this? Wait, I got to share my screen here. What's going on? Oh, okay, you guys can see this now, yeah? I'm sorry, I don't know what you guys are seeing. You guys could be seeing me running around in my pajamas for all I know. But don't worry, I'm actually dressed.
And drinking coffee. We do see
you. I'm drinking this is my second morning latte because I'm getting my money's worth out of the $600 coffee machine that I bought. $600.
Are you kidding? That better be a good machine.
Well, it is a challenge, shall we say, to make. Once you get good at it, then you're like hooked because you spent all this money, right? Like even this morning, I was having trouble getting the espresso to express. I don't know, whatever. And but yeah, it's a bit of a problem. But so let's see. I need to see the chart here. There we go. Okay, cool. So now, and if you guys want more, of course you want more, but I will probably do one more homework problem. And then if you have trouble with the homework problems, send me emails, and I will respond. I promise. And I just need a little motivation, to be honest, right? So today, I just have planned. I'm just going to go over. There's a huge sort of chapter on spectrophotometry, And a lot of this will be review for many of you, but some of it won't. And so if you can just hang in there and sort of just listen, and I'll try to make it interesting, but and we'll try to have it be as interactive as possible. But so just hang in there, and we're going to go over spectrophotometry today, and then we'll probably do applications next week, right? The homework on spectrophotometry is due a week from tomorrow. Homework 1 is, right? And then there's another one due a week after that. So we got a lot of time for it, but let's get on to it here. So you know, this thing is a hog of my real estate here. Let's see here. There we go. There we go. Let's sort of get it smaller there. So spectrophotometry, right, has a couple points in chemistry and then in science in general, right? And so in chemistry, it's the art of making measurements by using light absorption or emission. So you're all familiar with absorbance, right? And how in many cases, chemical concentrations are in proportion to the absorbance, right? Also, luminescence, when chemicals are putting out light, then their concentrations are oftentimes in proportion to their luminescence, right? But then in science, the idea of making measurements on molecules, making measures of the energy states of the molecules is done with photons, right? It's done with light. And you rely on some kind of extremely convenient aspects of nature, which is that light comes in these packets of energy. There are for each light frequency, there's a given minimum energy packet, and that minimum energy packet is called a photon. And depending on the frequency of the photon or the energy of the photon, it will or will not be absorbed by a molecule. And if it is absorbed, that means that the molecule has two states separated by that energy level, right? One occupied on the lower side and unoccupied on the higher side. So blah, blah, blah. And then we'll talk about all this other stuff. So, oops, come on, there we go. Beep, 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 beep. So here's some definitions. Spectroscopy, that's what I just described. It's like basically learning about molecules, right? Spectrometry is applying spectroscopy, and spectrophotometry is measuring concentrations. But don't worry about this stuff. This is just sort of like a little bit academic. A good example of spectrophotometry or spectroscopy, right, is thinking about ozone, right? So ozone happens when ultraviolet light from the sun photolyzes oxygen, right? So O2 can be, that bond can be completely broken, and these atoms can be sent on opposite trajectories by the absorption of a high energy photon, right? And when one of these high energy oxygen atoms meets a dioxygen molecule under the right conditions, it will form ozone. And then that ozone is relatively stable. And certainly you can have a bottle of ozone, and I've heard it's blue. That's not why the sky is blue. That's a different effect. So, uh, but then ozone itself absorbs a much broader range of ultraviolet light than does dioxygen, right? And so it basically is our shield, right? And one way to measure it is to use a spectrometer here on a satellite, and you can relate the intensity of light that reaches a detector directly from the sun to that of light which passes through the atmosphere, reflects off the surface, and hits the same detector on a satellite, right? And so you can I don't know why they say 270, right? 270 is probably everything that will get through the atmosphere. But you could theoretically go further further blue than this, right? So you could go down to about 200. But I'm sure that those wavelengths are pretty strongly absorbed. But in any case, this is one way to do it, right? You can measure the light that travels a direct path through empty space and compare that to light which interacts with the atmosphere, right? And the concentrations of ozone and hypochlorite and formaldehyde and things like that in the atmosphere will lead to certain characteristic absorption patterns in the ultraviolet light here. So ultraviolet is basically 350 and shorter wavelengths, maybe call it 400 and shorter. The 400 nanometers is violet, right? And then everything shorter wavelengths than 400 is ultraviolet, right? And so you can see here, ozone has a sort of a complex broad envelope, right? But on the red side, there's some spikes, right? And these spikes will tend to give away that's ozone creating that envelope. Hypochlorite has a similar spectrum, and then formaldehyde has a very complex spectrum, starting significantly redder around 350. Right? And it's the patterns of absorption that can give you the identity of the gas here. So we will actually talk in some detail about deconvolving these patterns. Now, let's see here. So you can measure ozone in the atmosphere, and then you can just see that over time, the ground and the satellite-based measurements of ozone over the Antarctic, right? So this is just on the very southern pole of the planet. It really bottomed out here around 1990, 2000, and the question is why. And Cindy will know, but some of you, others of you may not know because you weren't alive during the kerfuffle that this stirred up, right? And what happened was there's a NASA scientist named Susan Solomon who she spent her life studying gas phase kinetics of molecules. Sort of a what you might consider sort of a sleepy subject, But she measured this and then, oh my gosh, why is the ozone dropping so dramatically over the southern pole during like these, I think they were the Antarctic winters or something like that. But the cause that what's her name, Solomon? Yeah, Susan Solomon. The cause was traced to chlorofluorocarbons. Chlorofluorocarbons are molecules with only carbon and fluorine and hydrogen, right? And So there's one called Freon, which is used as a refrigerant, or was used very widely as a refrigerant. And the idea of using chlorofluorocarbons was actually originally put out by a guy named Thomas Midgley, right? Now, this is a hilarious story if you have a good sense of the macabre. But Thomas Midgley was a chemical engineer. He died around 1930 or 40 or something. But he thought he was like the world's greatest chemist or something, right? And the first thing that Thomas Midgley gave to posterity was leaded gasoline. And this is something that even Cindy might not remember, but leaded gasoline was a friggin' scourge. I mean, can you imagine tons and tons of tetraethyl lead getting pumped into the atmosphere? All because it prevents engines from knocking, from pre-detonation. You guys don't know what that is. That's a good thing. It sucks. When your car can't go forward because there's explosions happening before the pistons reach top dead center. So Thomas Midgley first gave us tetraethyl lead, then defended it tooth and nail, even beyond the point where he knew it was a problem. And people in the Chevron refineries were dying from handling this crap. And it wasn't until the 70s until they had unleaded gas, like unleading it is a thing, Oh my God. Anyway, so Thomas Midgley first gave us leaded gas, then he gave us friggin' Freon, which destroyed the atmosphere. How much damage can one guy do? Anyway, he wasn't a chemist. He was a chemical engineer, right? And he suffered from the engineering disease of thinking he knows everything. At least that's my contention. So, but the chlorofluorocarbons release chlorine, and chlorine catalyzes ozone destruction. And there's a really good chemical cycle there. It's not too complicated, but I guess we're not going to see it right now. So, on to particles of light. Now, when you get into light, we have an immediate conundrum as chemists and scientists thinking about it, right? Light behaves as a wave and as a particle. It's actually really fun to think about because it is the quintessential fundamental quantum wave particle, right? It's a wave and a particle, and it always scatters and oh, it's just really cool stuff. But the fact that light behaves as a wave means that we can separate it based on diffraction. So light can go through diffraction gratings, and it will separate by wavelength, right? So that's how we can separate out certain colors of light in order to put those colors through chemicals and see whether or not they're absorbed or emitted or whatever, right? And also light behaves as a particle or as a photon, meaning that there's a minimum energy at each frequency, and then only multiples of that energy exist, right? Every green photon is kind of like the same, and they have a certain amount of energy, right? And photons exist as oscillating electric and magnetic fields, right? And it's kind of crazy that you can think about it, and a lot of the basic diffraction-based qualities of light, the equations governing multiple reflections, lots of this stuff just way predated any kind of electromagnetic description of light, you know? And people had no idea that light was an electromagnetic wave, but they could already do all this advanced math with it. There was a French scientist named Fresnel who did a bunch of calculations. It was Huygens. There was other guys who I'm not really qualified to talk about, but whose equations I've used with great success, but who had no idea that light was an electromagnetic wave. They just didn't know. The electromagnetic part came after Faraday and Maxwell. They worked together. Faraday was an experimentalist, and Maxwell was a theoretical mathematical physicist, right? And Maxwell supplied Faraday with the measurements and the ideas, and Maxwell put them into differential equation form. And then they formed Maxwell's equations, which are incredible, an incredible set of equations. They knew that electricity and magnetism were mixed up, but they did not know how or why, right? They knew that a changing electric field would make a magnetic field, etc. But it turns out, guys, that this changing electric field creates a magnetic field because of relativity. You actually only need special relativity. So when this electric field changes, there's a relativistic effect that creates a magnetic field, which is really just an electric field from a new perspective, right? And then this guy can self-propagate. And this self-propagation is light. So light goes at a speed of 3 times 10 to the 8th meters per second. And this, by the way, is 1 over the square root of the magnetic permeability of free space times the electrical permittivity of free space. So this was figured out in theory right around the same time it was measured, I think. So that is a major triumph for physics to come up with this value. So lambda is wavelength, nu is light frequency. You multiply these two together and you get C, which is the speed of light. So blah, blah, blah. Okay, so whenever there's a medium other than vacuum for the light to go through, light scatters off the particles, and the stronger the scattering, the higher n, the n value is. And so n is called the refractive index, right? So even clear media like glass and air and stuff, they have an n value that's significantly different than 1. So 1 is the minimum value of n, and then n goes up from there, and n can actually be complex, a complex number which accounts for absorption of light, etc. But basically n is the refractive index, and it tells you how much light is slowed down, how much the wavelength is compressed in a medium other than vacuum. So it's a wave and it's a photon, or it's a wave and it's a particle, right? And the particle nature of light is what determines how photons interact with things like molecules, right? And the photon, there's actually a lot of research going on right now in generating single photons one at a time. And it's a challenging area. But, and it's challenging to detect them and challenging to make them. And there's lots of interesting sort of things like that. But basically, when you get right down to it, Planck, who was a turn of the century physicist, he came up with a constant to explain the weird behavior of black body radiation. And he had no friggin' idea what this meant. But he said, okay, well, he was a good accountant, right? And he accounted for the energy in streams of photons. And he came up with this constant by which you multiplied the frequency to get the energy per uh, per packet of light, per photon of light, right? And then Einstein came along and said, hey, dude, you discovered the photon, you know? And he was like, grumble, grumble. I don't know what we're talking about. But yeah, that's cool. And so uh, with the C and H and all this other stuff, you got a pretty good chemistry level description of the photon, right? And E, the energy of a photon is equal to H times nu. Nu is the frequency, right? And then nu is C over lambda. And then 1 over lambda is called nu bar. So E equals HC over lambda, or HC nu bar, pretty much sums it up for our description of light. And light, as you may or may not know, is an enormous, practically limitless spectrum of frequencies here, all the way from extremely energetic rays, which, you know, actually the limit here is that when they get ultra energetic, they create pairs of electrons and anti-electrons. They pair produce and they just separate. They create opposite momentum pairs of electrons and anti-electrons. And I don't know if that's how electrons came into existence or not. If it was, then we got to explain a lot of anti-electrons, or the absence of anti-electrons. But in any case, you've got the high energy guys here, gamma rays, which come from the nucleus generally, nowadays, right? X-rays, which come from the cores of atoms, ultraviolet rays, which come from the valence of atoms, the valence electrons, visible photons, which come from a type of valence, a low energy valence electron, and it accounts for all the variety of, No, I think I went the wrong way. There we go. Visible light, which accounts for all of the variety of colors that we see. It's all due to basically conjugated molecules. You know, all due to organic molecules with double, single, double bond alternating things. There's some inorganic compounds like permanganates and copper and whatnot, which have color due to DD transitions and things like that. But the great majority of what we see in our very limited visible spectrum of light is due to this type of electronic excitation. It's pi to pi star or n to pi star type transitions in molecules, right? Then going red from here, there's a big kind of a dark region, right? Well, it's actually a bright region where nothing absorbs this light, but we can't see anything in it because we can't see there, right? And this is an interesting sort of spectral range to exploit, right? And then you get further into the infrared and you start to see the vibrations of molecules, right? Where it's actually where the frequency of vibration and the frequency of light are the same. And under those conditions, E equals H nu not only applies to light, but it also applies to molecules. Isn't that weird? Like light photons, which have zero mass, and then molecules, which have a ton of mass, they have energy spacings in them, E equals H nu. Okay, anyway, I thought it was interesting. And then
Mind blown.
mind blown.
You don't want to interrupt the flow of knowledge.
Oh, thank you, thank you, thank you. Yes. Uh, thank you, Brandon. The flow of something anyway. So, and then microwave radiation, there's a similar phenomenon there, right? Where you have the rotational frequency of molecules is equal to the light frequency, and then those resonance points also you have E equals H nu type correspondence, and you can introduce light of a per frequency that equals a rotational frequency, and those molecules will absorb and also emit that frequency of light. Same with vibrations, kind of et cetera, along down the line. But mostly what chemists deal with is vibration and visible UV and X-ray absorption, you know? So it's not like we're so limited, but we're not completely unlimited here. So the absorption of light, okay, so it's been half an hour. I've been talking nonstop. You guys are probably about ready to kill me and everybody else in your near vicinity. So let's have a slight break for the sake of compassion. And let's do a little exercise. Let us just say, for example, oops, I will go to my document camera here. There we go. Oh my, everything's lighting up just fine. This is my document camera. And let us just say that we have a molecule, let's say it's formaldehyde, COHH, right? And it has some non-bonding electrons here. It has some pi electrons. And it also has some pi star orbitals, right? Pi star orbitals. These orbitals are generally vacant, right? And let's say that the energy, the potential energy of one of these non-bonding electrons relative to these are the non-bonding states, these are the pi star states. Let's say that this energy gap is equal to, let's say, 3.7 eV, or maybe 4.7. And say, what wavelength would that correspond to? So let me go ahead and grab a browser and say, Planck's constant. Let's get Planck's constant, right? There it is in joules, right? So I'm going to jot it down. 6.626 times 10 to the minus 34 joule seconds, or 6.58 2 times 10 to the minus 16 EV seconds, right? These are just different units to put this guy in. An electron volt, this is the energy to take an electron from from 0 to minus V in volts, right? That's an electron, or minus 1 volt, right? 1 electron changes potential energy by minus 1 volts. So the answer to this question then is E equals H C over lambda, right? So lambda then is equal to HC over E, right, which is equal to 6.5 or 6.6 times 10 to the minus 16 EV seconds over 4.7 EV times 3.0 times 10 to the 8th meters per second. Oops. Sorry, this gets pretty ugly. It probably comes out super shaky on YouTube too. I'm trying to fix this. I just don't know. I have an unsteady desk. Yikes. So let me see if I can get this done here. 6.5 times 10 to the minus, 16. Enter. 3 times 10 to the 8th times 4.7 divide 1 times 10 to the 9th. Oops. This came out to 42 nanometers. That can't be right. What did I do wrong here? It's probably
Professor,
420. Yes.
it looks like you used the wrong Planck's constant. You have the H bar instead of.
Oh, thank you. Thank you.
Yeah.
Sorry. What's the right one?
4.135 times 10 to the negative 15.
Thank you very much. So I should be able to take this and multiply by 2 pi. Multiply by 12, basically. 42. This is about 500 nanometers. Yay! Thank you. Saved by the bell. So anyway, this is how not to go through this type of problem, just in case you're curious. So like, for example, then this means that a molecule has this energy spacing, right? If you see an absorption at 4.7 eV, or actually, yeah, 4.7 eV, or 504 nanometers, right? This is 504 if it's emitted. Oops. This is green. Right? So if you see green light, you know that that corresponds to a transition in a molecule of about 4.7 volts, right? And this is why I like electron volts, because there is conceivably a battery that you could make a battery with a voltage of 4.7 volts, right? With an open circuit potential change of 4.7 volts. The wavicle, I like it. So, and then like that quantum phenomenon of that energy change then is very macroscopically observable. There's some statistical parts that you have to get under control in order to calculate the exact voltage, right? There's the Nernst equation, for example, where you can throw the concentrations in there. But basically the quantum of energy, it corresponds to a wavelength of light that those molecules could emit if the electron were to simply jump from reducing agent to oxidizing agent. Then they would emit that green light. And that green light there at 504 nanometers is, you know, it's it sort of connects two macroscopic things, right? Like a battery voltage and an observed color, right? And that's what the electron volt does for you in that way. Shut up. You guys are picking on me. I'm just kidding. You're not no one's picking on me. I'm just struggling to understand everything. Okay, so Planck's constant. Oh, there it is. Absorption spectrophotometry. Oops. Oh shoot. I gotta find this thing again. There we go. So so basically what I said earlier was that absorption and emission occurs between states in a molecule, right? You know, there's a bunch of things you can say about these types of diagrams, but the ground state is very important because that's basically where all these processes start, you know? There's always a starting and an ending point to an arrow, you know? And in general, you know, molecules at room temperature start in their ground states and they end up in an excited state. And then when then emission generally starts from the lowest excited state, right? It's not quite indicated here, but let me do this guy just one better, just real easy, real quickly here. Oops. So let's see. Okay, I'm focused here. So, when you have a molecule, generally there's an electronic ground state and an electronic excited state. So this would be, you know, like the electronic ground state, like say, like a hydrogen atom, you know, it would just have all the electrons in their lowest possible states, you know, 2 electrons per orbital, right? And then if you had a molecule, right, then there would be electronics, call it n equals 0, n equals 1. Then you would have vibrational levels associated with each electronic level, right? Right, so this would be electronic. And then these guys here would be they would be vibrational levels, right? And spectroscopy normally starts here. And then it goes up to some state there, right? So this arrow corresponds to an absorption of light. And the wavelength of that absorption is equal to, okay, so E equals HC over lambda. So lambda equals HC over E, right? So this is energy here. And then generally what happens is that there's a fast non-radiative decay, right? So this squiggly line is for a fast non-radiative decay. And then that state there, it'll create a new arrow, a new radiative arrow, which goes down to there, or goes down to there, or goes down to there. Right? So these guys here, these are emission. Right? And so both the absorption and the emission line are wavelengths, let's say, tell you about the internal energy states of the molecule. Oops. Oops. Sorry, hold on. There we go. So does this all make sense to everybody? Cindy, Katie, the only two people with their cameras on. Oops, darn it.
Hello, I'm here. May I ask a question, please?
Oh, you're not here.
I'm
You're not here. All I see is a name.
Oh, I'm here. I'm right here.
There you are. There you are, buddy.
I'm just taking notes. If I were to turn my camera on, you would probably see my hair most of the time. So that's why I
You
didn't
can
turn
see my hair. I like to see your hair.
taking
My
notes.
God.
Okay.
Yes,
Right.
sir. Yes, sir. Talk
What
to me.
do you mean by both? May you go back to the string that you have against it?
Sure. Hold on just a sec. I'm going to try to get this guy back. Oops. Oh my gosh.
What
I
happened?
must have closed it. Come on. Wait. There we go. Hold on. There we go. This one, right?
Yes. So both are, what is the E stands for, sir? Both or the bottom, right? Both or E emission.
Oh, both absorption and emission. Sorry. Yeah, this is absorption. And emission wavelengths. I tell you about the internal energy of the molecule.
And then what is the DU or about, may I ask?
This?
So emission wavelength, and then DU about intro.
This says tell.
Oh,
This is
my
tell.
internet. Yes.
Tell you about the internal energy of the molecule. So basically, if the molecule absorbs at this wavelength, right? That tells you that there's a state here and a state here, you know? Tells you that basically that there are two states, one filled and one empty, that are separated by this energy level, you know? Then if it emits at this wavelength, it tells you that there's a state here and a state here, you know? So you basically, you can, like a detective, you can put together a picture of the molecule, of the internal energy states of the molecule.
Oh, so every time it absorbs and emits, you have two states, one full state and one blank state. The blank state is where it starts from.
Exactly right. Exactly right. I mean, it has to start in a filled state, you know, goes from filled to empty, you know.
Yes, sir.
Okey-dokey. Julios. Okay, so so let's see here. I covered all this stuff. We sort of did this one in a very stupid way. You guys can kind of review this. There'll be questions like this in the homework. 100 kilojoules per mole. Kilojoules per mole, you know, basically these are the favorite, like I like electron volts, some people like kilojoules per mole, but so you basically just multiply by 6.023 times 10 to the 23rd. And you go from these really tiny values to hundreds of thousands, right? So that would be 1 times 10 to the 5th joules per mole. And but basically, what we're talking about when we're talking about measuring light is we have some source, we have a wavelength selector, a sample, and a detector. And how's everybody doing? I hate this. I feel like I'm just talking into nothing here. You okay,
Yeah.
Hanging on every word.
Hanging on every word. Okay. Yes. All right. So, you know, the source here, if it's a laser, then there's much less wavelength selection to do, right? Because lasers are super bright right at one wavelength, you know? But if it's an incandescent source, like a light bulb or even an LED or something like that, then generally what you need is you need some smooth monochromator here, right? So this white light can go in and just say green light can come out, you know? And then you work with these wavelengths one at a time, right? So what comes out, you know, ideally here is, hello, Solomon. How's it going, buddy?
Good, doctor.
So what comes out here is you've got some incident light energy P0. It goes through a sample of length B. Hey, Jonathan, how are you? I have not seen you. Are you a friend's assist?
And I was here last class in the video.
Oh, no. I mean, I know. I just like haven't seen you milling around the basement of Duncan Hall or anything. Are you a chemist or are you a forensics guy?
No, I'm a chemist.
Excellent. We need more chemists. And I'll tell lots of cool forensic stories when I can remember them. But,
Cool.
So P0 is the incident light. P is the transmitted light intensity, right? At any given wavelength. Oops. What happened? There we go. And I've lost my ability. Oh, I guess I just got to click on it. Okay. So then, and the way that the wavelength selector works is sort of analogous to this thingy here, right? This picture gives us some idea of how that might work, right? So this is a transmission grating. It's basically just a piece of plastic or some transparent material with a lot of lines etched onto the surface. And the lines have a spacing such that, you know, around 500 nanometers, there's an angular dependence to the one wavelength slip, right? So that light that's just transmitted is said to be diffracted at order 0. And then light that's diffracted at order 1 has an angle dependence, right? And you can actually see here on this color plate that there's violet, you know, indigo, green, blue, green, yellow, orange, and red. Can't really see the orange there, can you? But each of these wavelengths comes out at a distinct angle, right? And so if you can just observe just at this angle, set up the optics so that only this angle, whoops, come on, go back. There we go. So that only this angle goes into the sample, and then only that wavelength and angle comes out, then you can basically make this absorption measurement where you measure P0 going in and P coming out, right? And in practice, the way that you measure P0 and P is that you use a special sample called a blank, and you measure P0, the light that's transmitted through the blank, and then you replace that blank with a sample and you measure the light that's transmitted through it, P, right? Okay, so we're gonna skip this. This is just like blah, blah, whatever. So this is more about that. Okay, so concentration and light intensity ratio is related to concentration, right? The value of P, the light intensity, the light power really, that gets through a sample, and P0 that gets through a blank is related to the concentration of analyte if that analyte absorbs some of that light, right? So essentially, there's a logarithmic relationship, right? You can define a thing called the transmittance. Transmittance here, which is P over P0. And the absorbance is the negative log of that value, right? So let me ask a quick question about the domain of transmittance here, right? What is the maximum value of transmittance that you could ever see in a normal sample?
1.
1. Exactly. That's the maximum value you'll ever get in a non-super radiant medium. And what is the minimum value?
0, or can it be -1?
Exactamundo. We have to use the white supremacy symbol here. I'm sorry. Ah.
Is that what that is?
Yeah, I know. It's horrible.
I don't know these things.
I know. I didn't know it until I started seeing this Capitol riot shit. Like, oh God, damn. No, I don't ever want to do that again. You know, but it's like, you know, but it's also rude in Colombia for a completely different reason. Like y'all. Okay, all right. Quick aside here, right? We all know like this thumbs up, right? That means,
Yeah.
that actually goes back to the Roman emperors who would say, like, let the guy live, you know? But actually, let him live was actually like this.
Yeah.
You understand, and then kill him was like this, it's like, whoa, right? But then there's all kinds of interesting symbols, like this is peace, right? This means peace. But this is basically FU in England, right? And you know where that comes from? It comes from the wars that they used to have with the French, and what they would do to the French soldiers that they caught. You know what they would do? They would chop off the fingers, exactly.
Ugh.
So they couldn't operate a bow, right? That's how they lost all their soldiers, was from bows and arrows. So they would chop off the fingers, right? So, and so we know we have a good education now on hand symbols. But anyway, so transmittance goes from 0 to 1 normally, right? And the negative log of transmittance then, so the log, what is the log of 1? What is the base 10 log of 1? And you can say it. You know,
Yeah, I'm afraid to use hand signals
no,
now.
I have to make the white supremacy symbol to do that.
0.
Right? So the log of 1 is 0.
Yeah.
Now, what is the log of 0?
Doesn't exist.
Okay. Absolutely right. How about the log of 0.001? Take a small number. Tell me the log of 0.001.
That would be a negative.
Mm-hmm. Let's see here. I'm going to go with t, and then log of t.
Do you want us to see this?
Yeah, I'll give it to you in just a second.
Oh, okay.
Yeah. I'm sort of getting.
Making sure your computer didn't get stuck.
Yeah, I'm gonna make an exception and be semi-prepared this
Oh.
time. So
Ooh.
transmittance here. If transmittance is 1, the log of 1 is 0, and the negative log of 1 is also 0, right? So this is absorption. Okay. If we have 0.1, the log of 0.1 is -1, right? And the negative log of that is obviously +1, right? 0.01 is -2, and so that's 2, right? And so you can see how as the absorption goes up here, right? Let's say we had the negative log value of -10, right? Then what this would correspond to would be an absorption of 10, but the actual transmittance would be an extremely small number. This is not measurable. Right? So this is one of the first cautionary tales about absorption spectrophotometry, right? Is that 0 is less than A is less than about 2. This is good for absorbance, right? Outside of that range, the absorbance measurements are suspect. So there's lots of interesting sort of corollaries to this about the noise and absorbance versus absorbance. Right, so you can take if you want to talk about sigma sub A over A, right? The relative noise in an absorption measurement. It actually starts large, goes down to a minimum, and then goes up. So there's an optimum signal to noise ratio. Absorption, P, I think that's a P, right? Measurement. And it's usually around 0.3, but you know, basically it's less than 1. You know, between 0.1 and 1.0. So if you want, that's the most precise are in this range, right? Doesn't mean you can't use them outside that range. It just means that that's where they're best. Okay, cool. Yeah, I'm gonna make this bad and then better again. There we go. Okay. So, I'll go back to the PowerPoint now and we'll finish up this part of the presentation for today. So let's see here. So absorption and concentration are related, right? The absorption and the concentration have this logarithmic relationship, right? And it makes sense, right? Because some things are completely opaque, like no light gets through them, right? You know, and in that case, P is close to 0, right? And that's real common, you know? And then things that are completely transparent, where P is roughly equal to P0, right? They'll have an absorbance of 0, right? And then you can just define a molar absorptivity epsilon that places the concentration. Now, epsilon and C are connected by the units in C, right? Not a big deal there, right? But then here's a bunch of aqueous solutions. Yay. These are dilute. These are concentrated. Okay. Oops. Let's see here. You know, here is a pretty weird thing, right? Is that they're saying that, oops, darn it. That they're saying here, I don't know if this is true. I honestly don't know if this is true. certainly, Beer's law applies to monochromatic light. No problem there. And if you're changing concentration and there's no weird equilibrium happening, right? Then this applies, right? But also the concentration has to be below 10 millimolar? What? That does not seem right to me. But I don't know, maybe we can do a test or something of this, you know? Have to have some weakly absorbing species, you know, with an epsilon value of around 1, right? And then we can test this. So let's take that on this semester. Okay.
In our first lab.
Yeah, actually we could. In our first lab, actually, if we use something like copper sulfate, we could do this with our first lab, because copper sulfate has a weak blue absorption, right? It has a high solubility, so it's perfect for this test. Normally we use in our first lab we use oh, it's my wife calling. I'm going to tell her to go away.
Aw.
Hey, honey buddy. Oops, hold on. Hey, babe. You know what I'm doing right now? No, I'm not working on your homework. You know what I'm doing? Yes. He doesn't even get a kick out of it anymore. Jeez. Oh my God. She used to Skype me. She used to Skype me. And this was when I had an in-person lecture, you know? And I would just like put it on screen and like, and she'd be like, oh, how you doing? And then she.
Oh, you can still do that on Zoom. Just share that part of the screen.
I could totally do that. I could totally do that. But she doesn't Skype me anymore. So she's learned. She's learned not to do that. But anyway, I just like to be weird and mean, I guess. So yeah, normally we use a blue molecule called crystal violet. And crystal violet has an epsilon value of around 100,000, right? And so you have to get it around 1 micromolar to get an absorbance of 0.1, right? But if we use copper sulfate, then we can get these really large concentrations, and we can see whether this 0.01 molar thing is true. And, you know, I know Dan Harris. I've met Dan Harris, right? And he's like one of these kind of eggheads that they're always goddamn right. You know, no matter how outrageous what they're saying is, you know it's right. I think he just lives for that shit. But so I'm probably wrong here, but I have never heard this before, that an analyte has to be 0.01 molar. Oops. Has to be 0.01 molar or less to have Beer's law apply. So anyway, maybe we'll figure that out, right? And then, and this is the last thing we'll say today, right? Is that if you have a solution that has more than one thing in it, that's something that chemists frequently encounter, yeah? And in that case, you can take the epsilon values and the concentrations for each species and you can add them up. That will give the absorption, right? So if you have 3 absorbing components, 3 independent epsilon values, 3 different absorptions, 3 epsilons, how many concentrations can you determine? 3 absorbances, 3 epsilons gives you
3 concentrations.
3 concentrations. Excellent. Good. We will do more of this very shortly. Thank you very, 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 very much. I'm going to sign off now.
Wait, Dr. Chow, can I ask you a question real quick before, like after class is over?
Absolutely.
Okay, thank you.
You're going to ask.
Hello, Dr. Taro. Can I have one question after the lecture also?
Oh, you want to ask him after lecture? Why don't you ask him now?
Đây nè.
I can't make everybody go away if that's what you're wanting, you know?
No,
Bye, Karen.
for the homework number 4, when I do the calculation and I put in the number is, I think it's 11.542 or something, but it's say it's incorrect. I don't know why, but I calculate it right in the table.
I know. So this is something that if you could basically, if you could just send me, if you could just like send me your work, like, I don't know, like somehow make a PDF or something and just send it to me and say, hey, Dr. T, what's wrong with this? Why does this stupid software tell me I got 0 points on this when I should be getting 100 points, right? Just send me that message and I guarantee you I will either find the problem and I will tell you what the problem is, or I will give you 100 points. Well, I'll give you the full points, right?
Okay. Okay.
Okay. Two most common problems. Sapling does weird things with rounding and significant figures, and they'll knock off points for that. And then the thing I do the most is I just wrote a number down wrong when I was doing my calculations, and then it's like it kept telling me my answer was wrong. I think, but no, I keep plugging it in. I'm getting the same thing.
I'm sorry. I hate this whole thing, and I will fix it. I promise I'll fix it. But anyway, we're actually thinking about transitioning to a different homework setting, but I'm not sure if I'll get to it this semester. Sorry. But basically email me and you can just type it in an email. Type your answer in an email and say, hey, this is what I did. This is what it said. Give me my points, man. And I'll give you your points.
Yeah. And then where did you put the solution, the YouTube video for the homework problem?
It's on Canvas. It's right there.
I didn't find it.
Well, okay. I'm sure it's there. I made it there. I made it be there. Hold on. Canvas. Boopity boop. Okay, so here is student view. It's under lecture and homework recordings.
Oh, okay.
Yeah, I just did it yesterday. I just started this yesterday. So you go here, then you'll see that there's homework recording chapter 4A. This is just one of them, you know. So okay.
Okay, thank you, sir.
Sure. Solomon?
Oh, I was wondering if I can switch to the Thursday lab group B because there's a spot.
I do not see why not, but let me just look into it a little bit.
Okay, thank you.
Excellent. Is that
Professor? No,
Yeah.
I have a question about the form, the DocuSign for the COVID.
Oh, right. Yeah, where is that?
So no, I have 2 lab classes and I basically signed one for my other lab class. And every time I try to ask for a new link, it just brings up the old one that's already been signed and I can't actually sign a new one.
Okay, I will take care of that.
I think-
Okay.
Do you need to sign both labs, Dr. Terrell?
Yeah, you do.
Oh,
I think
okay.
both
Okay,
labs?
find the other one.
Because
Well, I'm teaching 3 labs, but they're all Chem 155 labs.
Mhm.
Well, that's it. So, all righty, guys. Are we good? Have you had enough?
Yeah, I just want to make sure I can get into the Thursday group B lab and then I'll be good. That's all.
I will try. I will try.
Okay. Thank you, doctor. Have a good day.
Thank you, Dr. T.
Bye-bye.
Yeah.
Dr. T, wait,
No, no. What is it? What is
wait.
it?
May I check in with you about the textbook questions, sir?
The textbook question?
Oh yeah, the sapling thingy, sapling questions.
Oh,
Did they reply back to you, sir? May I ask?
did I email Sapling for you?
Oh no, you emailed the textbook, that gentleman. I was wondering if he replied back to you.
So what was your question and what was?
I don't know if he replies back yet.
You
There
don't
was
remember?
something about the voucher. Remember, Dr. Sarah? The
Oh, okay.
voucher.
Ah, right. Actually, they did get back to me, and
Yes.
oh God, let's see. Here.
What did it say, sir? What did it? Are they okay with it?
Hold on. This is gonna be. Oh yeah,
How many emails do you have a day, sir?
I have plenty.
God.
Let's see here.
My God, that's a lot. That's
let's
a
see.
lot. Dr. Terrell, do you happen to know if I graduate, if I'm graduating this semester, do you happen to know if I need a graduation card, sir?
You have to apply for graduation. That is one thing you do have to do.
I
Are
did.
you a BS chemistry
I
major?
did. Yeah, I did.
Biochem or BA?
It's right there, sir. Yeah.
No. I'm asking you. You changed the subject, so I'm
Oh,
asking
BS.
you.
BS.
Are you your BS?
BS.
Oh, okay. So you're mine.
Yes, sir.
So we need to apply for graduation.
Wait, are you in charge of graduation?
No. I'm your advisor.
Oh. Wait, I thought Dr. Michikowski was my advisor.
Okay. So you're
we-
you're a biochemist.
Yes, sir.
Your BS Chem bio, concentration bio.
Yes, sir.
Okay. So you talk to Dr. Midge and and say, hey, I need to apply for graduation. And I emailed them about this, but I can't find it now. They did get back to me. And oh, here it is.
Whatever. That's
Here it is.
what happened? Yeah.
Like to provide the information.
No.
You can bring in the code, which allow for use. Okay, I'll try this. I'll try putting. I'll reply to them with the information, and I'll get back to you as soon as I hear back from them.
Please, sir. Thank you. And Dr. Terrell, I don't want to be behind your course. Is it so? I was wondering, may I work the homework problem with other students who have done it already? They can share me the problem.
Absolutely.
And then, is it the same number?
What?
Is it the same number, same problem for everyone, sir? I can do them and then I just submit once I have the saplings already.
You can do it. The numbers change
Oh, okay.
slightly, so you have to kind of pen in the new numbers when you actually put them into submit them. But everything else stays the same.
Okay, got it.
Yeah,
So the
sorry.
number changes.
The numbers change. It goes from 0.0273 to 0.0265. Molar, that type of thing.
Okay, got it.
So they change slightly. So the answers change slightly. But I'll put in this information for you. Okie dokie.
Thank you so much.
Okay, cool.
Yes.
Excellent. One thing at a time here. We'll get you taken care of.
Thank you, sir.
All righty, bud. Talk to you soon.